Hello boys and girls, welcome to another episode on our YouTube channel. My name is Craig. I'll be your host in this vlog where I discuss and rate beer and attempt to repair a typical electronic consumer good that you might find in the average South African home. Today on review we have this Urban Legend from Mad Giant IPA. Weighs in at 5.5% alcohol. It's not filtered, so there is yeast in the bottom, so I'm going to pour it very slowly. I suspect it's going to fall into the American IPA category, so let's open it. I'll pour it. Interesting. Anyway, today on the bench we have a little PID controller one of my electrical colleagues managed to damage. Let's get the bench set up. We'll take it from there. So here we are on the bench. We have this little PID controller. Let's see if we can get that in focus for you. TOHO Electronics CN40. What this thing does is it has a little input over here, a temperature sensor, and you can give it a set point and it will turn an output on and off to keep that temperature control. And what my colleague did is he confused this with the wrong model. He thought this thing has a potential free contact, which we could see out here, but what it actually does is there's a solid state relay output, and one must always be careful when working with solid state relays, because what is actually happening is that this equipment is now sourcing the power. It's not you giving it power and it switches a contact. This thing is actually giving you the power. So he put his own mains on and he's blown something up inside, and I don't think it's going to be very difficult to find. What we'll expect to see buggered is a series pass transistor or something like that. Back onto the beer for today. IPA, American IPA. I'm going to say, I'm guessing it's going to be American IPA, style 21 in the BJCP style guidelines. IPA categories for modern American IPAs and their derivatives. This does not imply that English IPAs aren't proper IPAs, or that there isn't a relationship between them. This is simply a method of grouping similar styles for competition purposes. English IPAs are grouped with other English-derived beers, and the stronger double IPA is grouped with stronger American beers. The term IPA is intentionally not spelled out as India Pale Ale, since none of these beers historically went to India, and many aren't pale. However, the term IPA has come to be a balanced, defined style in modern craft beer. Either way, I'm going to say, if we look under style 21, we have 21A American IPA, 21B Specialty IPA, and that's where we start going into different colors, derivatives, whatever, Belgians, whatever. I'm going to stick with 21A for now. So style 21A American IPA, overall impression: a decidedly hoppy and bitter, moderately strong American pale ale, showcasing modern American or New World hop varieties. The balance is hop forward with a clean fermentation profile, dryish finish, and a clean sporting malt, allowing a creative range of hop character to shine through. On the bottle, the description: bold and fruity, loaded with tastes of guava, papaya, and mango for those who like it loaded and loud. Now remember, this is a bottled beer. I don't know how long it's been on the shelf. I haven't contacted the brewer to find out how their coding works. There's definitely malt aroma. Not malt aroma, hop aroma, sorry. There's some nice taste going on in here. But anyway, let's just move the beer out of the way, and let's take this thing apart, because there's no point in putting power on. We might as well just take it apart and see what's going on. To open it, there's only, as you can see, there's 2 little screws down there. What I suggest you do, if you're not familiar with electronics, is take a picture beforehand so you can see how the casing goes back together, what you've taken out. So what I'm going to do, I'm just going to open this thing and we'll come back. Okay, here we are. We've taken it apart, or taken the casing off, and really what we can see, if we look down there, well, there was a transistor that lived down there. That's gone to hell. But we can see at the back here, that one seems to have a little bit of a bead on it, and well, clearly there's some black markings on this little component down here. I don't know what it is. It's probably some other sort of a transistor. Hopefully that's not the case, because this one looks like it's more power. We probably have some voltage regulation or switching transistors down here. Either way, what we're going to have to do, I'm just going to zoom out a little bit, is we're going to have to split this board, and I'm not quite sure how we're going to split it. I haven't really looked at it. What we can see, if we look down here, clearly there's been some repairs on this before. Somebody's put some bodge wires in here, clearly where they've destroyed traces. So it looks to me like this is not the first time my electrical colleague has buggered this up. Thing to note, in South Africa, when we talk about electrical engineers and electronic engineers, they are 2 different animals. This is electronics, the stuff in your wires coming to a house and that sort of thing in factories, big stuff, big power. That's electrical engineers. So I just want to bring the casing in and show you the label. Interestingly enough, what we can see is you've got your AC supply up here. Let's just zoom in a little bit and show you a bit more clearer. So pin 1 and 2 AC supply. But 3, 4 is either normally open with a common, or what we can see in the case of a solid state relay is, oops, it's a positive and a negative. 2 different things. The normally open in the common, you would be putting your voltage on here. You could switch it through to drive whatever. In this case, the circuit is sourcing the voltage. Very interestingly, you can either have a thermocouple, which is quite interesting, or you can have an RTD wired into a thermocouple. Is just 2 dissimilar metals. We won't go into too much detail, but what they do is the 2 dissimilar metals are bonded at one end, this pointy bit normally, and as the temperature changes, the dissimilar metals twist and they give you out a voltage, and that will give you an indication of the temperature. It's not linear. An RTD is a resistance temperature device, normally a PT100. All that means is it's a resistor made out of platinum, and at 100 ohms it's indicating 0 degrees Celsius. As the temperature rises, the resistance will change. It will increase again non-linearly and will indicate the temperature. But that's the major difference between the 2 is obviously temperature ranges and response time. RTD is a lot slower to react to temperature change than what a thermocouple is. So anyway, let me have a look at the board and see if I can split it, and we'll come back for that. And here we are again. Believe it or not, actually very simple to split this board. What you might have seen in the previous shot, you've got these little pads, and these other little pads up here, and they were solder bridged. So I've just taken a little bit of solder braid and some flux, and you can see just sucking that up, it's released that side. So if I switch the board around to give you an idea, you have the same things here. So all I'm doing, I'm putting in a little bit of solder flux down, just like this, nothing fancy. I'm taking my soldering iron. I'll try and give you an idea of this on the camera shot. Let's see if we can. I'm just laying it down, just like that. I'm just sucking up all that solder. Of course, this is difficult to do under the camera, so what I'm going to do, I'm just going to continue and take all those off, and then what should happen is this board will come out, and then we'll come back and take it from there. Okay, there you have it, boys and girls. We've split the board. We just zoom in a little bit, and obviously we can see the damaged areas down here. The little transistor's gone. We'll have to find out what it is or what it was. I really don't think we're going to find circuits diagrams for this, but that shouldn't be a train smash. If these guys have built this board properly, it will be common. What we just need to figure out is where it is in the circuit and what it's doing. If it really is a transistor, or might be a voltage regulator or something, which are very highly doubtful. So let me clean it up. I'm just going to use a little bit of isopropyl alcohol, and we'll take it from there. One thing that's very interesting about this Mad Giant beer, normal American IPA, when we talk about bitterness, they talk about 40 to 70. Now, this beer is not bitter at all. It's very fruity, very, very fruity, and it's got some very nice flavors. I do get the tropical fruit that they're talking about. I really get that in the taste. Very nice, but not bitter at all. They talk about the alcohol range. They said they weighed in at 5.5%. That is on the lower end of the IPA scale. American IPA, our vital statistics, IBU is 40 to 70, SRM 6 to 14, ABV 5.5 to 7.5. So really they're on the bottom end of the bitter. Well, sorry, correction, they're on the bottom end of the alcohol, but there's no ways that this is even close to a 40 IBU beer. A very drinkable beer. No, make no mistake. I mean, I poured this, and to get to this scene, I think really we're not that far in. And if I had to take a guess, I would say it's probably taken me 15 minutes to drink that beer. So definitely, no bitterness there. But anyway, let me clean the board up, and we'll take it from there. Right, so we've cleaned up the board a bit and zoomed in a little bit. What you can see is I've got my multimeter here, and I've got it set to diode test mode. There's our little component that's gone. I looked at the components around it, and the first digit I can barely see on this one, so I'm guessing it will be the same as these two, and they mark 13Y. 13Y is a SMD SOT23 package. It's I think it's a Zener diode, a 13 volt regulator, I'm not sure, but anyway, what is important, I'm just going to zoom out a little bit. This is going to be a bit difficult to do under the camera maybe. I'm just going to measure between those two legs there, and that's a dead short. That's the emitter and the collector. This is 2SC1384 NPN transistor. And if I measure between the base and the emitter, base to collector, come on, go in there. Okay, emitter, collector. Oh well. Either way, that is a dead short. That transistor is given up the ghost. So what I'm going to do is I'm just going to desolder it. That's not too difficult. There it is. It's those 3 little pins up there. What I use to desolder is this little desoldering sucker pump. Nothing fancy. So I'm going to just pull that transistor out and then we'll come back to it. Okay, here we've taken our little unfortunate NPN transistor out of 2SC1384. From left to right, you've got 3 legs. You see the front of the face is half, the back is rounded from the data sheet. From left to right, pin 1 the emitter, pin 2 the collector, pin 3 the base. Now, NPN transistor, very simply, put your multimeter in diode test. You short the 2 leads like that. You have a short. I'm just going to measure across, well, I'm going to try under the camera, the emitter and the collector. Come on, Craig. It's sticking to my fingers. There you go. The emitter collector is shorted. The emitter base is shorted. So that transistor is definitely giving up the ghost as well. I don't believe that I have any of these in stock. So what I'm going to do is I'm going to go out, order these. We'll come back once we've got some replacements and put them in, and we'll continue with our repair. Right, boys and girls, it's a few hours late on our repair, and I realized, just looking back over the footage, there's some things I haven't actually explained to you. For example, that transistor, what is a transistor? We've looked at diodes, we've looked at capacitors, we even looked briefly at a transformer, but how did we know that little transistor was gone? And that little package, obviously we can see it's blown, but how do we know what it is? Similarly, that resistor down there, I don't know if you can see, but the markings are gone off of it. It's also a blown open circuit. So what I need to do is I actually need to draw this circuit for you and show you on paper. But before I can draw it for you and show you on paper what it does, I need to first explain to you what a transistor does, and it's not a difficult component. Our beer, the Urban Legend, Mad Giant Urban Legend IPA, let me say, fantastic beer. I've been drinking it the whole day. I think I've done 6 of them now. The only issue that I have is I don't believe that this is an IPA. It is not bitter enough to fit into IPA region. And I thought maybe it was a couple that I had, then maybe I have the same batch. The numbers on the bottle don't tie. You've got all this beautiful tropical fruit thing going on. Very nice, fantastic, nice aromas, but the bitterness is just not there. So what I will do Obviously I have to order these components that I don't have, so I'll do that. But then what I'll do is I will pop in tomorrow into my bottle store to get a few more to see, is it maybe just the batch that I've had that it's aged a little bit or whatever, because I cannot give you a BJCP rating for this as an IPA. It doesn't even come close to an American Pale Ale, never mind India Pale Ale. The bitterness is just not there. Anyway, let me get the book out. Let's run through transistors quickly, and then we'll be on the same page. Right, here we have the book out, much easier. This transistor thing, what is it? Well, we've dealt with a diode. If we remember, let me try and get my hands under this tripod. If we remember our diode, very simply put, had a symbol looking like that, and that was it. If we put a positive voltage here, more positive in respect to there, current will flow. But what is this thing? A diode is actually made up of two chemical, or let's say a P and an N material. Can we see the similarity? If we put a positive here, a negative here, our electrons will actually flow through, and we'll have a current flow. A transistor, funny enough, is very similar to this. What they do with a transistor, and we're going to deal with a NPN transistor just to make it simple. We have an N, we have a P, and we have an N material. We have some funny names for these legs. The P in an NPN is going to be called a base. That N will be the collector, that N will be the emitter. Now, we're going to start with the NPN transistor because it's the easiest to understand. An NPN transistor, if we look at it like this, is basically two diodes back to back. There's a little bit of quantum and stuff that happens in there, but we don't need to worry about that. If we draw this symbol for an NPN transistor, it will look like that. An NPN transistor, I'm going to again put the leg letters in. That'll be our base, that'll be our collector, and the point with the arrow will be our emitter. Now normally an NPN transistor is known as a current sink. So normally that point will be tied to ground, and whatever we're trying to do will be over here. Now what does this transistor do? Well, a transistor is a magic thing. It allows me to put a small voltage over here with respect to that voltage, and typically that volt drop is 0.7 volts, and you would find this in a data sheet. It can be called a base emitter voltage. What is magic about this? Let's just work with 0.7 volts. So if that is ground, that's 0 volts. If I put 0.7 volts here, and I start putting a little bit of current into that base, I will switch this on. But it's more than that. We have a thing with a transistor called a saturation and a transistor gain. Normally this gain they call HFE, and it's approximately equal to 100. It can vary, it could be way more, 200, 300, but we typically work with 100. That means the current flowing through here, I need 1/100th of it flowing in here to drive that. Now that is magic. If I turn this thing on into full saturation, in other words, turn this transistor hard on, I might need, let's say, 1 milliamp here to switch 200 milliamp. Now that is magic. By varying this current in here, in this leg, I can vary the current flowing in here if I don't want to switch it hard on. If I want to actually change the current flowing through here, keeping that voltage constant and varying that current, I can vary the current flowing through here, but with this gain. In other words, I'm amplifying that signal. So our lowly little transistor, we can do two things with it. We can use it as a hard switch to switch things on or off, or we can actually use it as an amplifier, and that is a common application of a bijunction transistor. We call these bijunction because there's two junctions. There are many families to, well, there's not many, there's a few families to the transistor, but we're not going to go into that. We are just looking at the bijunction transistor and the NPN family. For interest's sake, the PNP works the opposite, and that would be a current source, but we're not going to go into that now. The easiest to understand is the NPN, and if we can get our head around putting a little bit of voltage on the base with respect to the emitter. Remember, it must just be more positive than that, and that's why I've drawn a ground there to make it easy to understand. So if that there is 0.7 volts, that is 0 volts, and by putting a little bit of current in there, I can switch this on, and by saturating the current here, I can turn this full on, and that is a transistor. So what I'll do, I will take the circuit, and I will just trace this out and draw a little circuit diagram so that we can actually understand what is happening in here. But what you can see, that transistor was an NPN transistor. I measured from the collector to the emitter, and I had a dead short. I've swapped the polarity of my probes around, and obviously doing this on diode test, swapped them around, and I had a dead short. That means this transistor is finished. The way to check this thing would be to put your multimeter and diode test, put your positive probe on the P, measure to the collector, measure to the emitter. If I get a diode drop here and a diode drop here, that's fine. If I swap the terminals around, I make this now the negative lead, and I measure here, I should have open circuit and open circuit. And in all cases, in an NPN transistor, regardless of the polarity, because this base is not switched on, I must measure open circuit. And that's how we measured to find that the transistor was shut. So anyway, what I'll do tomorrow, I'll get some more urban legend, and we can see if it's just a bad, or not a bad batch, it's a batch that's a bit aged, a bit matured. Like I said, I'm enjoying this beer. I'm drinking it like a cool drink, but it definitely doesn't fit into the realm of an IPA. I'm sorry, if I look at the style guide, even 12C, the English IPA, the minimum IBU is 40, and this is definitely not a 40 IBU beer. 40 IBU beer, you will know that bitterness lasts and lasts. But it's a well-made beer. I'm loving it. I love all the flavors in it. The drinkability for me is fantastic. But we'll get everything done and trace this out and get some more. Order the parts and everything. But for tomorrow we'll just trace it out, do the do the circuit and explain the circuit while we wait for the parts, and then replace them. And then we can repair this little controller and get it back home. Alright, boys and girls, we are on the bench. Just before I show you the circuit, I've finished tracing it out. Here's our points down here, 3 and 4. Those are our outputs. Well, you can see point 3, what we're really interested in, comes into this block. You've got a thing here marked JP. It's a jumper. You've got a big square block around this, which is actually marked I think RY1. There's a little diode there, but you can see there's a piece of track missing here. What is important for our circuit is that little transistor there, that little transistor there. We know that one we took out, which is blown. That one's blown in half. We come to this resistor down here that we don't know what it is. We've got a little capacitor going to ground and a little resistor going to ground, and that snakes its way up all the way to that point there. I'm just going to flip it across. What you can see on the bottom, there's these two little bridges put in, what I actually thought was somebody that bodged it, and I still think that. So what the designers done is they've created one board fits all. Either you are going to bridge that jumper and that jumper and that jumper and that jumper down there, and you will have a solid state output. In other words, you will source the 12 volts, which is what they've done. Or you take those jumpers out and use that voltage to drive this relay, which will now switch to our outputs. So I'm just going to take this out the way, zoom it out, and here we can see our circuit. What is important to note, the output of the circuit is rated at 12 volt DC, 600 ohm. If we go and calculate that backwards, I equals V over R, simple Ohm's law, we get a value of 20 milliamps. For now, ignore this stuff going on here. What is important to note, 3 comes through a jumper, through that resistor capacitor network we saw there. It comes up to this transistor here, it comes to this transistor here. We've got a capacitor down here, rated at 470 microfarad, 35 volts. We've got a Zener diode over here. We'll get into the Zener diode. Works almost the same as a normal diode. We put positive voltage and negative voltage with respect. It will conduct, it will block the voltage in reverse, but it's got a thing called a Zener voltage. Once that voltage meets the Zener voltage, that means this diode will now start conducting in the reverse. We have another transistor up here. Now this circuit, to understand, is not very difficult. We have a PNP transistor here. We have an NPN transistor. Now remember, we said if I put a positive voltage on the base, more positive with respect to the emitter, the transistor will switch on. It will conduct current that way and that way. An NPN transistor, a PNP transistor, notice this one's pointing in, works the opposite. If I put a positive voltage on its base, I switch the transistor off. So I have to put voltage on it to switch it off, where an NPN, I have to put voltage to switch it on. So our voltage is coming here from our little switch mode and step down and regulation, whatever. It comes to that point, we switch it on from whatever this is protection on the circuit. It will tell us, okay, you can switch on, you cannot switch on. So this will in all likelihood come from our set point. When the PV, the process variable, and the set point meet, this one will switch on. Will actually switch off, because it's, again, it's a PNP transistor. So depending on their logic, it will switch the transistor off or switch the transistor on. By doing that, we'll switch this transistor on, our current will flow, and we'll switch this transistor off. why is this transistor here? That little transistor is the transistor with the three blown, the little blown legs. And you'll see I've got this RX, that's the resistor we don't know. Now this can only be a PNP transistor for a few reasons that will become apparent. If we go and look here now, I've drawn in the alternates. We have the jumper in here and the jumper in here. That's 0.3 and 0.4. So forget the stuff in the middle. The jumpers are in, so that's what's happening. The voltage will be on that point, the negative of that voltage will come back to the 0 volt or earth. The reason for this transistor here is if they put a relay in. Now I've drawn this a bit weird. What I'm saying is we can switch the voltage. Remember, if that transistor is on, it will switch that transistor off. Those 2 points are the same. I will energize this coil of the relay that will go to earth, the Z point. Basic induction, Faraday's law. If I energize this coil, it will create a magnetic field. It pulls iron, it pulls a little rod in that will close this point. It will close the switch. So if those points were taken out and that switch closed, I could have my own voltage that I want to switch. So I've drawn this better on the right hand side here. Point Z is point Z, the top end of our coil. Point X is the normally open of our contact that it's going to switch, and W is that point there, is the common of the relay. Now remember, it's jumpered, so if we took the jumper out, it means I could switch my own voltage like that. And what you notice where that track was blown, there's a diode, and there's a reason for that, and we'll come back to that now. If you remember, we said a capacitor stores a DC voltage. Well, an inductor, which is a coil, will store a DC current, and it builds up the magnetic field, and it resists the change in flow of current. The problem that happens is when I take the signal away from there, this magnetic field is still there, and it has to collapse somehow. If it doesn't collapse, if the current can't continue flowing, remember, it doesn't want to have the change in current. So if we took the diode out, well, the current has got nowhere to go, the resistance stays the same, so what is going to happen? The voltage must go up, and if the voltage goes up, whatever's switching this thing will be destroyed, and that's where we come back to this transistor here. Bearing in mind we've switched the circuit on, we've got a positive on there, that will switch a positive through, switch a positive onto there, it will switch that PNP transistor off, and we will source our voltage down here through our jumper. We'll have our 12 volt. Well, let's take the jumper out, we have the relay, we drive in the relay, bang, it energizes, that switch will close, we're doing whatever. Now for whatever reason, we take that signal away, this transistor switches off. That means the voltage here at that point is more positive than that voltage. This thing will start to conduct, so it will now switch on. That flyback diode will allow the current to flow through there, and we come back to our Zener. So that voltage spike that would have happened if this wasn't there, we had nowhere to go, and would have destroyed that transistor, will now go to that, and I think it's an 18 volt rated Zener. The Zener will now switch on and discharge that whole circuit back to ground. It's a very interesting thing, this transistor. So very clever little circuit from the guys that designed this. Quite interesting that we can either put jumpers in or just let me bring the board back in that block, take the jumpers out, and then drop a relay in there. So we're still stuck with this RX that we don't know. Up here, the resistor that's blown. Oh, that can only be a PNP transistor. That's the one that's the 3 legs are blown out of. If we go down, I'm going to just zoom out a little bit, and we look at it, we need 12 volts at 600 ohms. That's what it can supply. In other words, 12 volts, 20 milliamp into our load. That means I need 12 volts at this point over here. Now what voltage can we have up here? Well, this specific transistor only has a 200 millivolt drop when it's switched on between the collector and the emitter, so that's negligible. So I still have 12 volts here. I need 12 volt 20 milliamp here. I go and look at that capacitor. It's 470 microfarad at 35 volt. It's just a smoothing capacitor or bulk storage capacitor. Remember, we said before, we normally double the capacitance value for the voltage we want here. So if I go and reverse this back, let's say I took, I'm just going to do it out of the screen, 12 volt. Let us say that coming through there, coming from that transistor, is 18, well, before, on the collector, the transmitter. Let us say the transformer, this little switch mode transformer upstream, is going to be, get a pen, let us say at that point we have 18 volts. It might sound far-fetched, but it's not really. We've got 18 volts, we've got 12 volts down here. That means we must drop 6 volts over that resistor, but we still need the 20 milliamp. So if I took the Ohm's law version of this, R equals V over I know I need to drop 6 volts divided by 20 milliamp. That resistor is going to be 300 ohms. And that makes sense if we go and look further in the board and we look at the components where they've got resistors. They've used the same value around at that part of the circuit. So I'm going to take these destroyed parts out. That one, that one, that one, we've already taken that one out. I'm going to order the spare components for that, and then and what I'm going to do to prevent further cock-ups from my electrical colleagues, I'll order a relay that fits this footprint in. It's a 12 volt coil, but that can drive 250 volts, let's say 10 amp, so my electrical colleague can have a potential free contact that he can use. I'm not going to do this online. It's simple. You've seen me take this out, these type of things out. It's just simple hot air. Clean it up, and what we'll do is we'll come back when we've got the spare components. We'll put them in and we'll test the circuit. Right, boys and girls, we are back. Finally, our components arrived from RS Components 3 weeks down the line. I don't know, somehow this is becoming really pathetic. You order components from RS Components South Africa, and then you must write a motivation because they must import it from Japan, and you have to write this whole motivation to clear their customs. That's a load of bullshit, but anyway. What we can see here, we have our little 12 volt relay that we're going to put in over here to make our little solid state output, well, not solid state, potential free contact for our colleague. Just to draw your attention to the size of the components that we are actually putting on. There's our two little PNP transistors that were shot, our little resistor that was blown out. This is a 2 rand coin to give you an idea of the sense of the size of the components that we've that we're putting on. Why I'm showing you the dimension of the coin to give you an idea. These components we're actually soldering by eye. We're not soldering this under microscope or anything like that. So you really don't need any fancy equipment to do it. It is quite possible to do it by hand, and a relatively decent soldering iron. You don't need any fancy equipment. So what I'm going to do, I'm going to set the board up. What we'll try and do is we'll try and solder this, or we'll try and solder a few components under the camera. Well, I will solder around the camera to give you an idea how we're doing it. One thing, I'm not going to be using the spray flux from RS Components, because finally this UV80 flux paste arrived. I ordered this 2 years ago through eBay, and it finally made its way through our postal service. So now I have it, and so what I'm going to do is move everything around, set it up, and then we'll get down to the soldering and get this board fixed so we can test it. Right, the first component we're going to put on is our little resistor that goes down here. All I've done, I've cleaned up the pads we saw in a previous shot, and I've just gone over it with some isopropyl alcohol because it's been sitting here for three weeks, so we want to get any oxidation, any rubbish like that off. So all I'm going to do, we're just going to pre-tin that pad, one little pad. We'll put down some flux paste, and then we'll put our resistor on. Should be pretty easy. We just tin the pad. We don't want too much, just like that. Clean the iron. And how I apply this flux paste is actually very easy. I just use, just make sure I don't get my hands in the way. I'm just going to use a toothpick. We'll apply a bit across, and we'll apply a bit to the other pad. Now this stuff is magic because it's tacky, and that is ideal, because what will happen is when I take our component and I put it here, it will actually make the component stick down. Nice little trick for younger players. So I'm going to put our component on. Try not to get distracted through the phone, because it is a bit of a no-no to look through the phone when you're doing this. Just tack it in. Perfectly gone. There we go. One side down. So now we will move to the other side and just apply some flux paste again. We'll just rub it on. The flux is going to allow the solder to move under the joint. So let's see if we can bring that up a bit. There's our flux paste. There we go. We're going to put our solder in and bring our solder iron to it. Perfect, you see? Nice and neat. Of course, we can go back and straighten it up at the end of the day. And there we go. Our little resistor is down. So I will go solder in. These are the little SOT23 packages. Clean up the resistor, make it nice and neat, and I will show you what we're going to do with this relay for the broken track, and then we'll come back when we're ready for the relay. So let me just go and clean up our little effort here, because it's difficult for me to solder under the camera. I'm filming with my iPhone, so yeah, and this tiny little tripod. So I'll just fix up that little resistor. It was just to give you an idea. Put in these other little two PNP transistors that were blown, that little NPN transistor, and we'll come back for the relay. Alright, we're back. We can see I've cleaned up that little resistor, made it nice and neat. We've replaced that little SOT23 PNP transistor, that one as well. We can see to come around this broken track over here, I've just soldered a piece of bodge wire that the original repair guy put in. So because these are plated through holes, I'm going to pop the relay in, and when I solder it, the solder will flow and it will join that, so that will repair that little broken track. So I'm not going to do this on air. It's actually very simple. It's not like soldering these little SMD components, so it's not very exciting. So I'm going to solder that relay back in, check the circuit continuity, put the board back together with the other one, and then we'll come back and we'll test this thing and we'll see exactly. So boys and girls, here we are again. I've just put the two boards together with, you can see these pre-made up little jumper cables that I've put in. What we can see is the controller is giving us a ERR1, and if I look in the manual for that, it means that there is an error with the analog to digital converter. So I'm going to stop the repair right here. Why I'm going to do that is because we need to explain a few concepts before we go on about what it is we're trying to measure, how it works, and how that is converted, and what is all this analog to digital converter rubbish and that sort of stuff. I'm going to set up the scope. I just want to show you. You see, I've got my oscilloscope probe over there. I'm measuring the input terminals where the signal would go, and there's something very interesting going on there. So I'm going to just take out this little decade box that I've got here that I'm using to simulate the signal. Sorry for the bumping. I just want to show you a few things in here. So let's just move it over there and zoom in a bit. Now what we can see, my oscilloscope probes are here on the right, don't worry about that. That little relay there is just a error relay. Our signal comes in down here, it goes through this little black chip here, that's called a multiplexer or demultiplexer, but it's a specific analog multiplexer, demultiplexer, and that's why I'm going to stop the repair here, because there's quite a bit of explaining to do about what is happening, why is the signal what it is, what does this thing do, what do these things do, and to further repair the board. So I'm just going to set the shot up and show you the scope signal that I'm seeing, and then we'll finish with our beer review, because otherwise this video is just going to get way too long. So boys and girls, here's what I'm actually seeing on the oscilloscope. I've got the time base set to 5 microseconds. I've got my trigger, a little T over there, set because I just want to see these two double peaks. I've got a frequency count on, it's running at about 110 kilohertz, 100 to 110 kilohertz. I've got my voltage division set to 200 millivolt per division, and we're getting roughly 750 to 1 volt peak to peak. In other words, from that point to that point. I'm just going to show you the ringing. That is not normal. also what you can see is that the primary voltage is jumping up and down, up and down, up and up. In other words, the carrier voltage, and that is slightly problematic. So, like I say, I'm going to stop the repair here. We'll make a part 2. We'll explain what the other components are, or why we're seeing this, and go on to repair the measurement side. For those of you wondering at home, do yourself a favor, take the 100 kilohertz signal, take the inverse of that, divide it by 2, because you see there's 2 little peaks and you'll get your 5 microsecond base. So I might have told you in an earlier video, oscilloscope is a very nice thing to see voltage changing over time. It gives you a very good idea of the patterns and waveforms that are going in. So I'm going to set up the shot for our closeout and our beer review, because I think that's important. You might be wondering about the thing above the oscilloscope. This is for a future video. For those of you playing along at home and your girlfriend or your wife, your boyfriend, it doesn't matter to me, when your microwave or your cathode ray TV fucks out and you think you're the man or the lady about the house and you can fix everything, I'm going to show you why you should rather stay out of there. Notice the max voltage I can measure with this is 40,000 volt DC or 28,000 volt AC. I will show you in a future video what the hell is actually happening in your microwave and why you should just throw it away, buy a new one, unless you know what you're doing. So let me get the shot set up and we will finish our review of the Mad Giant. Right, boys and girls, and so we come to the end of another video. Our beer on review, the Mad Giant IPA. This beer has given me a headache of note. I tried to reach out to the brewer to get some statistics on the beer, and unfortunately, I don't know, maybe they're too busy. They didn't get back to me. The urban legend, the bottle says Mad Giant Urban Legend IPA, bold, fruity, loaded with taste of guava, papaya, and mango for those who like it loaded and loud. Unpasteurized, keep refrigerated, 5.5% alcohol, and that's it. If I look at IPA, American IPA specs, ABV, straight away, the starting ABV is 5.5%. Starting IBU, in other words, the bitterness, 40. Now, I'm sorry, this is not a 40 IBU beer. It just, I'm sorry, it doesn't come close to an IPA. That being said, I know many years ago, the owner of Mad Giant, or the guy that I know that owns it, Eben, was making an American Pale Ale, and I don't really know what happened to that, but this, if I take this beer, this would fit nicely into American Pale Ale, so I'm going to rate it as an American Pale Ale. You can shoot me, I don't particularly care. Remember, we used the style guidelines to tell us what the beer is. The thing is, we should not be trying to fit the beer to the style. The brewer should do that. So if I look at American Pale Ale, just the vital statistics, bitterness 30 to 50. Now that can be because in general the human tongue is at about 5 IBU either way. So even though I think this is probably about a 27 IBU beer, I think it would fit in that 30 to 50 if I give them benefit of the doubt on the bitterness. SRM color, yeah, 5 to 10, it's light enough. ABV 5.5 to 6.2, so that would put this right in the middle of an American Pale Ale. Now, the style guidelines for American Pale Ale: overall impression, a pale, refreshing and hoppy ale. Well, it's pale, it is very refreshing, and it's hoppy, it's not bitter. It's got sufficient supporting malt to make the beer balanced and drinkable. Yes. That is definitely, it's there. Aroma moderate to strong hop aroma from American or New World hop varieties with a wide range of possible characteristics, including citrus, floral, pine, resinous, spicy, tropical fruit, stone fruit, berry, or melon. Well, these guys have definitely gone the tropical fruit route. You get that, the melon aromas. It's not strong. It's not overpoweringly strong. It's not anything like I would expect from an IPA. And what is nice is that flavor imparted from the hop. They've done this very, very well. Carries through. Unfortunately, again, the bitterness is not there. Now, you can shoot me, but before we go there, there is a technique when you're brewing. The earlier you add the hops into your boil, the more bitterness it gives. The later you add them, the more aroma. The thing is that the utilization factor of the hops becomes less and less the later you add it into the boil. So to get the same bitterness, you would probably use 100 times the hops the later you put it in the boil. So I cannot see that you would be adding more hops than the batch of beer to get the same bitterness. But you will get a lot of, the later you put it in, you'll get a lot of flavor from the hop, and you will start getting a lot more aroma. Those are typically your late copper hops, the late hops you're putting into the boil. The aroma in a lot of IPAs is derived from the dry hopping addition. In other words, the end of fermentation, then we start putting in hops and letting the beer sit on the hops to absorb the aroma. You're not getting much flavor there. The flavor is caught out through the boiling process of making the beer. So like I said, this is no ways this is a 40 or 45 IBU beer. I think it's 45 on their website. Again, I didn't get a feedback from them. Appearance: pale golden to light amber, moderately large white to off-white head with good retention. Well, yeah, I poured it quickly. I didn't bother trying to create a head. Nice white head. Clear, but I haven't poured the whole bottle in. I saved the last bit for the yeast. Flavor: moderate to high hop flavor. Well, definitely, I love the flavor of this beer. I think this is about the 8th 4-pack that I've bought over the last 3 weeks to get my head around this beer. Typically showing American and New World hop citrus, floral, pine, blah blah blah, tropical fruit. So yes, we know they're getting those fruity hops. Definitely they're getting in here. The papaya, that melon, that green thing, I don't know what it's called. I'm liking it. There is a bit of citrus. I can't remember. I met Eben somewhere once when he was starting out. He's a fantastic brewer. I think he's very partial to Simcoe hops. But no, I don't want to speculate. Low to moderate, clean, grainy malt character supports the hop presentation. Well, they've got that spot on. It is a very nice, very well balanced beer. This I cannot praise it enough. It's just not an IPA. Mouthfeel, medium light to medium body. Yeah, spot on. Moderate to high carbonation, I wouldn't say that, but moderate carbonation. Overall smooth finish without astringency and harshness. Well, there is no harshness. If you use hops in the wrong way, you can get that very astringent, vegetal, make your face feel like a chicken's pawpaw type thing. No, they haven't done that. This really is to me, it's and dangerously, very dangerously so. It's a session beer. I know in South Africa, if you put 5.5% on the label as your ABV, trust me, it has to be tested. That's what it's going to be. And that makes this thing very dangerous, because this you can, well, I can easily sit and pop this as a session beer. Oh, it is nice. Comments. Hopping styles can vary from the classic large bitterness addition to the modern late hop bursted examples. All variations are allowable. I don't want to guess, but I would say there was a little bash in the beginning of the boil with some bittering hops, and everything came into this towards the end, and I would say probably in the last 20 to 15 minutes to close. That's where they've got this flavor from, and it's really well done. It's a difficult technique to get right, but very, very, very nice beer. So as an IPA, I'm not going to rate it. It doesn't feature as an IPA. As an APA, they've ticked all the numbers. I remember many years back when they started, Mad Giant APA was one of my favorite go-to APAs. They really hit it on the nose, and then it sort of disappeared. I couldn't find it anyway, and it's come back, but this is different to that. That was a very citrusy APA. This has got it's like, and I'm not a fruit person, but I've stayed in enough hotels to know, it's like going to that buffet in the morning. They put all that fruit stuff on a plate, and then they put yogurt on it, and they put this. It is silky smooth, and you've got all that fruitiness going on. It is beautifully done. It's deceptively evil. It really is deceptively evil. Trust me, this is one of those beers you're going to open and you're going to pop it, and well, you can see in this little review, it's oh okay, my rating for style 18B American Pale Ale I'm going to give them 4.3 out of 5. It is well made for American pale ale. Beautiful. My drinkability, oh, 4.6 out of 5. I've got 2 4-packs left. I'm going to make a braai just now, and trust me, the beer will probably be finished before I've even got the fire warm enough. It is, it is a gorgeous, gorgeous beer. I described it to a colleague as, it's like having one of those, what were they called, those orangey nectar drinks, but the creamy sort of one in a beer. It is gorgeous. I'm going to stick to that. About the repair, I'm going to have to split it because we need to discuss a few concepts. It's not, I don't want to get into the theory too much behind it, but the concepts of what the measurement points are doing, and then we'll go on and repair a little PID control in part 2. As usual, guys, if you like what you saw and everything, you know, the buttons are below. If not, same buttons are below. If you want to discuss this beer, I'm very, very open to it. I smoke it stickend. Mad Giant, based in Joburg, in the Joburg CBD, the Mabodeng precinct. I know they've partnered with somebody that does their restaurant service, but their brewery is open. You can actually see it. I used to work in the Joburg CBD. I used to go there quite often during breaks and catch have a pint and whatever. Fantastic place to visit. Check it out. As always, guys and girls, be safe. Take it easy. We'll catch you in the next one. Cheers.